This is the second half of Chapter 7 on solutions. The topics for Part 2 are percent concentration, molarity and dilution, and properties of solutions, which will include solutions, colloids, and suspensions, colligative properties, and osmosis. So we'll start with solution concentration, and we're going to start with percent. So mass percent, which is abbreviated M/M, is the concentration by mass of a solute in a solution. This is used commercially, used in hospitals. And in order to calculate the mass percent, you need to know the mass of the solute in grams divided by the mass of the solution. And you notice the mass of the solution is the sum of these two. So I can replace grams of solute plus grams of solvent with grams of solution. Now you have to be careful here because many times they will give you the solute and the solvent, and you have to know that you need the solution to actually do the calculation. You can also measure volume percent, and we do this if the solute is a liquid. And this is common, for instance, with alcohol solutions. You have maybe you might have some rubbing alcohol at home. That says 70% on it. So that means 70% alcohol out of 100 milliliters of solution. And so that 30 milliliters is probably water that's left over. We can also have mass volume percent, and that's kind of obvious by the equation here. So let's take a look at the example. So if I weighed out 8 grams of potassium chloride on the scale, and then I added enough water so that the total mass became 50. So that 50 now includes the 8 grams of KCl. So that's going to be the grams of solution. So if I wanted to calculate the mass percent, I write down my formula and replace the data, and I get 8 over 50 times 100, I'm going to get a 16% solution. Now what didn't matter that it was 8 grams of KCl, it could be 8 grams of anything, as long as it dissolves in water, and I would have got a 16% solution. All right, let's go through another example. So let's say you made a solution by using 15 grams of sodium carbonate and 235 grams of water, and we want to calculate the mass percent. So we want to copy out the data and label everything. So the mass of the solute is 15 grams of sodium carbonate. The solute is always a smaller mass. The mass of the solution, you have to add them together. Again, this is where people make mistakes, I know. So you get 250 grams. Write down our formula and just plug things in, and we get a 6.00%. So you multiply 15 times 100 and then divide by 250. Pretty straightforward. Right, now here's an application of that formula. Let's say you wanted to know how many grams of sodium chloride you need to weigh out in order to prepare 225 grams of a 10% mass sodium chloride solution. So you already know what you want the concentration to be of your solution. You already know that. And you already know how much of the solution you need. You need 225 grams of it. So the question is, how many grams of sodium chloride would you use? So we're given 225 grams of solution, and we have our percent, or known as grams of sodium chloride. So the first thing is to really take that percent apart. So percent means 10 grams of NaCl for every 100 grams of solution. Now we want 225 grams of solution, so that's going to be more than 10 grams of sodium chloride. Now we're going to use this fraction here as a conversion factor. So when I take my given information, the 225 grams, notice how I just multiply it by this conversion factor. And let me get my pen down here. The red color, and you see the grams of solution cancel out, and I wind up getting 22.5 grams of sodium chloride. So that's how much sodium chloride then I would weigh out. I would add enough water until the total mass became 225. Alright, so here's one for you to try. Solution is prepared by mixing 30 grams of sodium carbonate and 235 grams of water. Calculate the mass percent. So these are the three possibilities. So you want to pause the video at this time and try this problem. Okay, here is a solution to it. So here's the problem again. So I want to determine my quantities of solute and solution. So the solute is 30 grams, and the solution is the sum of these two, because it's only 235 grams of water. So that's going to be 265 grams of solution. All right, my expression is my formula. And then I'm going to just plug in my data, and I get 11.3%, and that's the answer. So how did you do? Hope you got it right. Okay, now molarity is the next concentration value we're going to take a look at, and this is used for chemical reactions because you get moles of solute. So molarity means moles of solute per liter of solution. We can write it as a fraction, as you see there, right here. And let's say I wanted to make up 1 molar solution. So this is how we write molarity. We use the capital M for molarity because there's no symbol for an element with just an M in it. So 1.0 capital M means 1.0 molar sodium hydroxide. That's the word we use, is molar. And that means 1.00 moles per liter. Now, do you need a mole of it? Well, you do if you want a liter of it. So let's see, here's our example. So over here, let's say you weigh out how much a mole of sodium chloride would weigh. That would be 58.5 grams. That's its molar mass. And then we put it into this flask. This is called a volumetric flask. You see there's one little line up here. That's the only graduation on it. And then you add water until you get to that line. And that means you'd have a liter of it. And that's how you would make up a 1.00 molar, and there's the word down here for you, molar sodium chloride solution. So let's say we have a problem based on that. So let's say we have a half a liter of a sodium hydroxide solution, and we know that it contains 6 grams of sodium hydroxide, and we want to know what the molarity is. So copy out our given information. We have grams of sodium hydroxide, and we have 5.5 liters of solution. This is what we want. So moles per liter. So we need moles, which we don't have yet. We're going to have to get that. And we need liters, and we have that. So the molar mass of NaOH is 40. So that's sodium plus oxygen plus hydrogen. And then we get the molarity. So to get the molar mass, we're going to take my given information, and I'm going to multiply it by 1 mole over 40 grams. That's going to give me 0.15 moles of sodium hydroxide. Now the grams would cancel out. And then I'm going to take my 0.15 moles of sodium hydroxide and divide it by my liters, and I get 0.300 moles per liter. Or I can write it as 0.300 capital M. And that's how you find the molarity. Now here's a question that's an application of the molarity formula. What if I have a certain volume of a solution, in this case it's 125 milliliters, and I'll say I know what the molarity is, it's 0.720 molar KCl. And I want to know how many grams of KCl are dissolved in it. So I copy out the given information. Right. Now in order to get grams of KCl, I'm going to have to find moles, because I can go from moles to grams then at the end. So let's see, I have liters in my molarity formula, and this is milliliters. So I'm going to have to convert milliliters to liters here. So to do that first, 1,000 milliliters per liter, and that gives me 0.125 liters. Now I can use my molarity here. Remember, this is a conversion factor. So I can take my number of liters and multiply it by moles per liter. The liters will cancel, and I get 0.0900 moles of KCl. I don't want to round that number off because I'm going to use it in the next step. Once I have the moles of KCl, I can multiply by its molar mass, which is 74.6 grams per mole, and that will give me my answer in grams, and I get 6.71 grams. So molar mass of KCl is, of course, the atomic mass of KCl of K plus Cl. Now here's one for you to try. What's the molarity of 0.225 liters of a KNO3 solution that contains 34.8 grams of KNO3? So pause the video, give it one a try, and then come on back and see the solution. Okay, here is the solution. Here's my question again. I'm going to find the moles of KNO3. The molar mass would be 101.1. So again, that's potassium plus nitrogen plus 3 times the oxygen. So I'm going to find my number of moles. So you see how the grams of KNO3 would cancel out. And I get that many moles. And then I'm going to take my number of moles and divide it by the liters, which I was given. And I wind up with my 1.53 moles per liter. Pretty straightforward. Hope you got it right. All right, the next topic is dilution. This is very common in all the sciences. We buy concentrated solutions and then we dilute them for our purposes. It's just cheaper and it's easier for storage to just buy concentrated ones. So in a dilution, we're going to be adding water almost always. And when we do that, the volume goes up, as you can see in our example here. Here's a small volume down here. See the line? And now we have a much larger volume. We've added a lot of water to it. And as we do that, the concentration goes down. Here you can see there's a lot more particles in a smaller volume. Here there's many fewer. So the concentration always goes down. This is one of those inverse relationships. So here's an example using orange juice. I guess you can still buy this in a store, though I don't think many people do anymore. Years ago it was very popular. So you can buy frozen concentrated orange juice, and actually they get rid of the water and then they can what's left. So look out, they're very, very thick. And 1 can of frozen orange juice concentrate added to 3 cans of water gives you 4 cans of orange juice. And that's what it would say. So again, easier to store it, takes up less space, mix this up and then you'd use it. So in the initial and diluted solution, the amount of the solute, which can be measured in grams or moles, is the same. It's just the concentrations and the volumes that are going to change. So the concentration always goes down as the volume goes up. So percent, we could use C1V1 equals C2V2. C just means concentration, and V for volume. The initial would be the 1s, diluted the 2s, and for molarity we would have M1V1 equals M2V2. Now technically it's the same formula. And so we're going to be using these when we want to calculate or answer some dilution questions. So here's an example here. What volume of a 2% mass volume HCl solution can be prepared by diluting 25 mL of 14.0 mass volume HCl solution? So I want to copy out the data first and label that. So let's get a better look at it. So what we're doing is we're starting with a very concentrated solution, 25 mL of it. We want to add water until the concentration drops down to 2%. So let's look at the difference in the numbers here. 14 to 2. So that means that the concentration is going to go down 7 times. 14 divided by 2 is 7. So if the concentration is going to go down to only 1/7 of what it was, that means the volume is going to have to go up 7 times. So I bet 7 times this number is our answer. Let's just go through the solution. So here's my formula. I'm going to solve it for my unknown by dividing both sides by C2. So that'll cancel out there. Then I'm going to plug in my values. And what do I get? I get exactly what I predicted. Because you see down here, the percent would cancel. And the 2 would go into 14. 7 times, and 7 times 25, that's 75. So if the numbers are easy, sometimes you can see what the answer is to these questions. Now here's one for you guys to try. Let's say we have a 1% HCl solution. You want to prepare that from a 10% HCl solution. You're going to use 25 mL of it. Oops, so we'll go back. So here's your problem. Give it a try. Come back and check your answer. All right, and here is the solution. Here's the problem again. Copy out the data and label it. So let's just look at the numbers. They're easy numbers. Here, 10% to 1%, so we're dividing 10 by 1. So if I divide 10 by 1, I should be then multiplying this by 10. I bet my answer is 250. So, I start with my formula. I'm looking for V2, so I'm going to divide both sides by C2. Like that. And then the C2 would cancel out. That's how I get over to here. Okay. Then I plug in my data, and I get exactly what I predicted. Okay, not too hard. All right, here's another one for you guys to try. What is the percent of a solution prepared by diluting 10 milliliters of a 9% sodium hydroxide to 60 mLs? So I'm just going to start you off with the data chart and have you finish it from there. So if we copy out the table, look what we have. Starting with a 9%, we're going to use 10 mLs of it, and the volume is going to go up to 60. So how many times is the volume going up? That's how many times the concentration will go down. So let's see if you can finish it off from there. So pause the video and then come on back and check it out. Okay, and here is the solution. So this time we're going to divide both sides by V2. So if I divide by V2 on both sides, here's my V2. I'm writing with the mouse, and that's not the easiest thing here. Sometimes it's easy, and sometimes not so good. This is what we wind up with, and that's how we go over to here. Now I'm going to just plug in my data, and I get 1.50. So remember, and you can see that the volume milliliters are canceled, so this is like, say, 1 over 6. So the volume went up 6 times, so the concentration goes down 6 times. Well, we can do the same kind of questions using molarity. So here's one for you to try. What's the molarity of a solution prepared by diluting 0.180 liters of 0.6 molar HNO3 to 0.540 liters? Now you might think we have to convert liters to milliliters, but we really don't. We just have to have the same volume. So pause the video, come on back and give it a try. Okay, and here's the solution. As we compare our table, when we want to check it out, we can see that the volume is going up. So if you were to divide this into that, you see it come up 3 times. So the volume is going up by 3. That means this should go down by 3. So I bet the answer is going to be 0.200. So up by 3, down by 3. So let's see. We solve for M2 by dividing by V2 on both sides. Plug in the numbers, and exactly what we predicted. So you see how quick this can be. You can even shorten your own solutions for these after a while.